Hello everyone, thank you for joining this presentation today. My name is Andrew Bowman. I am a research mechanical engineer with the U.S. Army Engineer Research and Development Center located in Vicksburg, Mississippi. Today I will present on some of our work on structure property relations of damage in polymers by atomistic simulations. This work was done in concordance with my PhD work, so I want to thank some of these members here for their contribution and help. So the URDEC is a branch or research lab for the U.S. Army Corps of Engineers. So we do mostly civil works and infrastructure work such as bridges and dams, along with some military engineering for like weapons effects. But we also have a basic materials research component, which is what this work falls under here. And the goal is to use basic research to inform some of this higher level infrastructure and military engineering that we need. So here we're looking at nanoscale, the nanoscale behavior of damage and deformation in polymers to get a better understanding of some of these effects. So the motivation of this work is the recent advance of nanomaterials and nanotechnologies and the very complex structure property relationships that we see at the nanoscale. We know nanoscale behavior is highly influenced by things like strain rates, adiabatic and frictional heating, and interactions at free surfaces and interfaces. So we want to investigate some of these mechanisms, things like healing of the polymer at the nanoscale, high strain rate features in front of the shock front, and even more complex features when you introduce things like phase-separated lamella or clusterings, or even look at metamaterials. All of these have very complex structure property relationships at the nanoscale. So we want to be able to use multiscale modeling in order to investigate some of these effects. Here we use MD simulations to look at the nanoscale behavior of things like loss of entanglements, bond breaking, damage, and in general just high strain rate mechanisms. We can use that to either inform directly a macroscale model or go through a mesoscale to look at things such as fiber matrix bonding, hard, soft phases, interfaces of crystal amorphous regions. But the overall goal is to use this information that we gather at nanoscale and mesoscales to bridge the macroscale, either in the form of rate equations or direct coefficients to put in macroscale models, so we can look at more structural things such as ballistic or blast penetrations that we see here. So here we have just a generic curve for a polymer. Up here we look at amorphous polyethylene, and as that's deformed, we see the accumulation of free volume or damage within the system. Eventually that leads to disentanglements and bond breaking within the system. All of these are related to each other in complex fashion. And we want to use this force field called the MEAM or modified embedded atom method with bond order. And this allows us to have a high accuracy look at free surface formation and bond breaking and bond forming during deformation. So we will take a closer look at that in a second. So the problem is with some previous molecular dynamic works, they use a united atom model to look at damage in polymers. So here you take your explicit formulation of hydrogen and carbon atoms, you replace it with a single bead, and if you have more complex polymers, you might replace larger polymer segments with a single bead. You connect them via some kind of bead spring potential, and you can look at deformation that way. It does have some good applications. It reduces the number of atoms in your system, it removes hydrogen atoms so you can take larger time steps, and it has been shown to capture stress strain behavior, or especially yielding, quite well in polymers. The problem is that post the yield point, a lot of uncertainty exists because it doesn't do a good job at capturing free surface formation, and it underestimates the friction to friction contact that you would have if these hydrogen atoms were present. So here we show a comparison of explicit to united atom models. We see that the stress strain general shapes are very similar, but the United Atom model does not capture this free volume evolution. It predicts very low free volume, while an explicit atom model seen here would actually predict much higher free volume accumulation or damage in the system. So the response then is to use an explicit atom setup, and here we choose our potential to be the modified embedded atom method. If you're familiar with the modified embedded atom method, you know that it started with Mike Vasquez in the 80s as the embedded atom method to look at simple metallic structures. It was later modified to add the angular dependence, which then you can look at more complex metals and covalent bonds. And then finally, within the last few years, this bond order component has been added to look at double and triple carbon bonds, oxygen and nitrogen, graphene, materials like that. What's interesting about this is that it will allow us in the future to look at polymer metal interfaces using the same functional form between the two. So you have a much easier time of parameterizing these potentials. A lot of good metallic potentials already exist. And then we can look at these complex interactions or interfaces between polymers and metals, such as what you see here with this polyethylene liner sandwiched between these two metals. So the formulation of MEAM is relatively simple, which makes it quite computationally efficient, especially considering that Ester reactive potential. So here we have your typical pair interaction, where you have between atom I and atom J, your screening factor, which just allows for a bond directionality. But what's important and what's special about the MEAM is this term here, which is the embedding energy. So this represents the energy required to embed an atom into the bulk polymer system. So for example, if you take an atom that's within a cluster of chains, for example, that would have a higher embedding energy or background electron density because it's in that cluster of atoms, while if you took one that's at a free surface, it would have a lower energy. So you can capture locality effects of your atoms, whether they be at free surfaces or in clusters of atoms. So it gives a higher accuracy, and that's why the MEAM can capture things like void formation energies and surface formation energy and chain-to-chain friction very well, is because of this term right here, which is unique to the MEAM potential. And then we can add bond order to the existing MEAM formulation, which then captures fractional bonds for double or triple bonds. This particular work, since we're just focused on polyethylene, these bond terms are zero since we have a completely saturated polymer, but we are working on more complex polymers that utilize these terms here. So one of the major questions that I want to address here preemptively, that I get almost at every presentation that I've done, is how do you bridge MD results to the macroscale? What relevant information, what useful information can we get from these MD simulations that we can use at the macroscale, whether they be qualitatively or quantitatively, and particularly use them in macroscale models? So the answer is mainly that it depends, and that it's a complex, unsolved problem currently. So we have this macroscale experiment defined here, a global strain rate that leads to this global deformation behavior of this sample. We can look at a very small region, perhaps on the nanoscale, and then we can define here a local strain rate and a local deformation. The problem, and as we see with MD simulations, is that the global deformation does not equal the local deformation. The global and local strain rates do not equal. The fracture strains are not equal. All of this because the macroscale experiment is heterogeneous in nature, while the nanoscale simulation is homogeneous in nature. So for the macroscale experiment, during deformation, certain heterogeneities, whether they be voids or particles or even just high triaxiality regions, will experience higher levels of strain rates and higher levels of deformation than what the macroscale experiment would. And then the issue is that a mapping or a bridge between the nanoscale and macroscale has not been successfully established. I've seen a few attempts at it, but there's still a lot of uncertainty that involves here. So it depends on what you're trying to upscale. If you're trying to upscale the stress of this nanoscale simulation to the macroscale prediction, you won't be able to do it because you have a different deformation and a different strain rate. But if you're looking at nanoscale structure property relationships or nanoscale mechanics, such as how entanglements disentangle during deformation, how chains align themselves, nanoscale damage, things like that can be used in upscaling mechanisms because these types of strains are seen, at the macroscale around these heterogeneities. And especially if you have low strain rate dependence, then you can definitely upscale certain things. So it depends, and you have to be careful on what you upscale to the macroscale when you're looking at these MD simulations. So here's some work we've done about 2 years ago on creep and polyethylene using MD simulations. So it's high rate creep, but it was a way to study the creep behavior and how damage develops during creep. So we were able to predict primary, secondary, and tertiary creep here for polyethylene, and then we also were able to count the number of voids that nucleate in the system during that deformation. So what we found was in the secondary creep regime, we had this constant creep rate, which is what we should see, but we also were able to find that you had a constant void nucleation rate in this regime. So you can plot those two together and you find that at different applied stresses, they're directly related to each other. The slopes are the same. You just have a shift on this the y-axis between the strain rate and the nucleation rate. And both of these could be fit with a model, so we could, having the strain rate, we could then predict what the nucleation rate would be. We were also able to look and show that in the secondary creep regime, is the dominant damage mechanism is void nucleation. We see this rapid increase in the number of voids, but once tertiary creep happens and deformation starts to speed up, leading to fracture, that is induced by this rapid void coalescence, or the number of voids rapidly decreases due to these void surfaces merging. So we were able to provide both qualitative and quantitative information here using these MD simulations. We also could show that void nucleation was directly related to structural changes such as disentanglements. So if you're interested in this, please see this 2019 paper that we published in Polymer. But here for some current work that we're doing is comparing deformation of amorphous polyethylene to a vinyl ester resin. So we have a thermoplastic compared to a thermoset, and we want to compare and contrast how damage progresses in each system. So both of these systems are made differently, right? One is an amorphous polymer, so we pack them randomly into a box. Here for the vinyl ester resin, we have these different monomers, and they're added to a box, and then we have a curing algorithm that selectively cross-links them until we reach a desired curing percentage, and then we equilibrate the box to high temperature and anneal it, which standard and MD, and then we deform them. Here's deformed by just a constant strain rates. So we compare them to the same strain rate and the same temperature, and look at how voids or damage evolve during deformation. So to do that, we have to define damage. So here we can count the number of voids in our system during deformation. We can count the total volume of voids, and we know what the total volume of the box is. That allows us to define some damage terms. So first, we define the void number density, which is equal to the number of voids in the system divided by the volume of the box. So you have a voids per unit volume. Average void size is the total void volume divided by the number of voids. And then finally, void volume fraction, which is the ratio of void volume to solid volume, which is the most important term here for quantifying damage. For the model, we use an exponential growth law for nucleation that's typically used in the literature. Here, A1 and B1 are shown here as simplified constants, but they can be quite complex. So, for example, here in the parentheses, you would have B1, which is both temperature and, for example, stress state dependence, where you have nucleation and tension or shear or compression, if by chance your polymer forms voids during compression, which is rare, but it is possible. Here we have the average void size, again defined by exponential growth. And then we introduce this term called the coalescence fraction, which is a logistic growth equation. So this allows us to capture the downward trend in the number of voids. So there's a certain point in your simulation where the number of voids will begin to decrease as voids start to merge and coalesce into larger voids. So this allows us to capture that. So this effect is inherently captured in the simulations just by the number of voids and the average size of voids, but it's not inherently captured in the models, so we need to define an explicit term for coalescence. So here we use this logistic growth equation. And you multiply nucleation times growth times coalescence, you can get your total void volume fraction. Here, the equation looks like this. Your exponential growth divided by this logistic growth. So it allows you to capture the damage response, as we'll see in a couple slides. And that's the term that we're going to actually fit to our simulation results. So here we have the stress-strain response for our polyethylene and vinyl ester resin. Here, polyethylene deformed first. We see a well distribution of the damage within the system. And then we have deformation here of our vinyl ester resin. We see voids start to nucleate, and they nucleate in a localized region, eventually leading to this catastrophic failure, which is what we see here in the stress-strain response. You have a much more brittle-like failure of our vinyl ester resin, only about 0.75 strain. Our yield is much higher than the polyethylene, and polyethylene is unique that it doesn't exhibit any bond breaking during deformation. All the chain deformation is due to loss of entanglements during and entanglement pullout. So we don't see a catastrophic failure. We just see very slow, gradual pullout of chains, and in fact, that can last, for 500 or 600% strain. But we'll here show it up to 1.5. So very different failure mechanisms as we would expect. Very different stress strain curves as we would expect. So we do a good job at capturing that phenomenon. Then we can look at the damage. So we have our simulated damage, and then we can also fit a model to it. So the black and blue curves here represents damage for polyethylene and uniaxial and biaxial tension. So we wanted to investigate, stress triaxiality effects on the damage. So we see higher stress triaxialities causes increased damage, which is what we would expect. And then we look at the damage evolution of the vinyl ester resin here in red, in the red curve. All the curves are able to be captured very well with our damage model. Here we have our coefficients here. So we see that this damage model that we developed captures this nanoscale damage evolution with pretty high accuracy. So next we want to compare our simulated void volume response to some experimental work done by Giselle on characterizing the volume strain of high density polyethylene. So we see here that our uniaxial simulated results do a very good job at capturing the uniaxial experiment void volume evolution here in these red dots. So the experiments found that most of the damage occurs within the amorphous region of the semicrystalline polymer, which is why our simulations of the amorphous polyethylene do a very good job at capturing this type of void volume response. So we were quite pleased that our nanoscale simulations could capture this macroscale damage evolution, and we believe that using this model as a bridge from nanoscale damage to macroscale damage is, before we do that, we have to look at the strain rate dependence as mentioned earlier. So here we see that the yield stress is indeed quite highly strain rate dependent in polyethylene. But you'll notice that once post the yield, that the shape of these stress strain curves are very similar. So there's not much stress strain dependence in what's occurring in these plasticity events, things like chain alignment and damage, and that's evident here in this void volume fraction. So this elbow is strain rate dependent, but post that you have very similar responses, and you have a lot of overlap with these uncertainties. So it's slightly strain rate dependent, but there's not a huge disparity in strain rate in this, as we see like in the yield curves. So we are able to capture at different strain rates. You could capture very similar void volume fraction evolutions, which all match the experimental results that we saw earlier. So then we use those the calibrated nanoscale damage model and in this internal state variable plasticity model to predict fracture in this notch tensile specimen that we have here. So here we have this notch tensile specimen being deformed. You'll see necking start to occur, and then you'll see final fracture. And you see that our red curve does a much better job at predicting the experiments than the solid black curve that was published with this work. We get the failure strain, about 10% accuracy, which is much better than what they predict. What's interesting is that we are able to capture the fracture surface. So here, this is one snapshot before failure, and we see that due to high stress triaxiality, most of the elements in the centralized region damage or fail first, and then you just have kind of like a catastrophic shear-like failure around these barrier elements, which is what we see in this experimental fracture surface for polyethylene. You have this area of high stress triaxiality causing lots of void growth, and then you have more of a shear-like failure around the outside. So to conclude, we used molecular dynamics simulations to predict the nanoscale damage evolution of a thermoplastic and compared it to a thermoset. We were able to define a damage model to capture the evolution of nanoscale damage with each system, and we're able to get a pretty good fit for our simulated and model damage response. The nanoscale calibrated damage model was used to predict the macroscale failure and strain of a fracture surface in HDPE, and overall this method shows that nanoscale simulations can be used to inform macroscale models. And with that, I would just like to thank you for attending this presentation. I'll take any questions you have. If you have any specific questions, you can address them to this email address shown, and I'll be happy to answer them there. So thank you again.